Let's derive an expression for the gravitational potential energy of the star. This will be a useful quantity to know and be able to at least make an order of magnitude estimate of. Now, last time we calculated the equation of mass conservation by imagining building up the star in a series of spherical shells. And we can use this formalism to derive our expression for the gravitational potential energy of the star. Now, we know from Newton's law of gravity that the gravitational potential energy of 2-point masses is equal to minus Newton's gravitational constant times the mass of one object times the mass of the second object divided by the separation r between them. And it turns out that if you are outside of a spherical body of matter, then that spherical body of matter behaves like a point mass concentrated in the center. Right, so, for example, we can use formulas like this to calculate the gravitational potential energy of the Earth and the Moon. They're not point masses, but they behave like point masses mathematically. That's one crucial result in Newtonian gravity. So we can actually make use of this formula to derive the gravitational potential energy of a particular spherical shell given the existence of the rest of the star beneath it. Okay. So let us suppose that we have built up our star to a certain amount, and we've added one extra shell of matter on top of it. Okay. We are at a radial coordinate little r, and we have derived in the previous lecture that the mass dm of this shell is given by 4 pi r squared dr times the density at that point. And the mass inside of that spherical shell is given by this equation of mass conservation here. This is the mass inside of the spherical shell here. So the gravitational potential energy associated with these two masses, m of r and the dm that we've put on top of it, we can call this du, and it's equal to minus g times the mass inside radius r times dm divided by r. Okay. So we can substitute in here dm is 4 pi r squared rho of r times dr. So let's do that. 4 pi r squared rho of r dr. And this is equal to, the r here cancels the r on top, so this is equal to g m of r 4 pi rho of r times r dr. Right, this is the r that's left over after the cancellation here. So the total gravitational potential energy of the star is just the sum of all the potential energies that we get from adding successive shells on as we go work our way constructing the star from the center out to the surface. So we just integrate this from 0 to the surface. It's minus g. Let's write the constants first, and then rho of r, m of r, r dr. Okay, so to do this integral, you need to know how rho changes or behaves as a function of r, and how the mass changes as a function of r. And we don't know that yet because we don't have all the equations of stellar structure needed to solve for rho as a function of r and m as a function of r. But what we can do is make an order of magnitude approximation. And to do that, we can make a drastic assumption, but it's an assumption that is not going to give us an answer that is wrong by more than the order of magnitude. And that is, we can assume that we can replace the density by some average value of the density, some constant value of the density throughout, some representative value. So we can take it to be a constant, and that means we can pull this outside of the integral. Before we do that, with this assumption, we can also solve this integral equation, the equation of mass conservation, pulling the constants outside of this integral. We've got 4 pi rho average times r squared, r prime squared dr prime. So r prime squared dr prime integrates to r cubed over 3, so we get 4 pi rho average r cubed divided by 3. This is, of course, just the volume of a sphere, 4 pi r cubed over 3, times the density. So this is just mass is volume times density, as we would expect the result to be for a sphere of constant mass. The total mass of the star is just the mass inside the radius big R. In other words, the total mass inside the surface of the star. Okay, so that is just 4 pi rho average big R cubed over 3. Finally, the gravitational potential energy is given by this expression here. Let's pull out some constants. So we've got 4 pi rho average big G, and then we're integrating from the center to the surface. What's left? Well, it's just the mass inside radius R, which is 4 pi rho average R cubed over 3 times R dr. Okay. Now we can simplify this a little bit. These constants, if we pull this outside, we're going to start to get a messy collection of constants here. But this here is just the total mass of the star divided by the total radius of the star cubed. Okay, so we can replace this big M over R cubed big G, and then we're left with the integral from 0 to R of little r cubed, r to the 4, because we're multiplying r cubed by r dr. Okay. We can simplify this even further by replacing rho average here with, again, using this formula here, rho average is just 3m divided by 4 pi r cubed. And if we substitute this in here, the 4 pi is going to cancel with the 4 pi on the bottom here, and we're going to end up with 3m. We've got another m here, so it's m squared. We've got r cubed on the bottom here, which combines with that r cubed to give r to the 6 times big G. And then r to the 4 integrates to r to the 5 divided by 5. So this gets multiplied by big R to the 5 over 5. The R to the 5 here cancels with all but one of the 6 R's on the bottom. And we finally end up with minus 3 big G m squared over 5R. So let me write this out again more clearly. For a constant density sphere, the gravitational potential energy is equal to 3g m squared over 5r, where r is the radius of the sphere and m is the mass of the sphere. Okay. So we can take this to be an order of magnitude estimate for the gravitational potential energy of a real star.